All right, section 3.1. So let me first start by letting you know, it's called Numeration Systems, that the point of this section is to make you feel a little bit uncomfortable. That's on purpose. And the reason is because, number one, we want to have an appreciation for the number system we have to some degree, right? We're glad that we're not working in these different systems we're going to encounter. But also the discomfort that you feel is sometimes the discomfort your students are going to feel working in our number system because they're not familiar with it yet. And so there's some of that that's ingrained in what we're doing in this section too, okay? All right, so we're going to start by talking about our number system just a bit. Our number system is actually called the Hindu-Arabic Numeration System. And you probably didn't know that, unless you've just seen it in another class before this. That's what it's called. It's the numeration system developed by the Hindu and transported to Europe by the Arabic. Our numerals are constructed from 10 digits. Those digits are not 1 through 10. A digit is a single value. It's 0 through 9. Those are our 10 digits. The place value of our digits is based on powers of 10, the number base of our system. So we have a base 10 number system. I know you've heard of that before. It means all of our place values are powers of 10, right? So we have the tens place, we have the hundreds place, which is 10 squared. We have the thousands place, which is 10 cubed. So not all number systems are base 10 number systems. A couple of our systems aren't. We're going to encounter them. And I want you to recall how powers work, because we're going to see that coming into play. A to the n power means I have a multiplied together n times. All good? Okay, so students usually like the first number system. The first number system is called the Egyptian number system. And the most interesting thing about the Egyptian number system is that their symbols are a little interesting. They're shapes more than they are like numbers like we use. So they have, the first one is this sort of stroke or a vertical staff, and this has the value of 1. So it looks like a 1. That's pretty straightforward. This upside down, it kind of looks like our intersection symbol, right? This upside down U is a heel bone. Can you imagine that sort of being the outline of your heel? It's a heel bone. And it has the value of 10. The next one looks almost like an incomplete 9 or something like that. It's actually called a scroll. And the scroll is worth 100. Can you see what's happening in the value column as we go up? It almost feels like it's a base 10. I mean, and they are showing up in powers of 10, right? That's what's happening here. They don't use a place value system. We'll see how they use it, but these are powers of 10 showing up. The next one is the trickiest one, I think, to draw. It's called a lotus flower. If you've done contemporary math or some other resources, sometimes the flowers are not drawn this way. They're drawn a little bit differently. Not all of these symbols are universal. Kind of imagine, if somebody looked at the way that we write different ones of our numbers. So think about like the number 4, and you have people write the 4 like this, and people write a 4 like this. They're still both 4s, but they just have a different sort of feel to them. This is kind of what's going on with their number system, is that there's different resources that show different versions of these. So this is our lotus flower. What do you suppose the lotus flower is worth? 1,000 is it? The next one is one of the ones that I find actually the most difficult to draw. I don't know why. It's very simple. It's called a pointing finger. So can you imagine like this? It's like pointing like this, right? Pointing finger. What's it going to be worth? 10,000, is it? The next one, the resource that I used for contemporary math calls this a burbo fish. Our book calls it a pollywog. I've seen other books call it a tadpole. So at any rate, it looks kind of like a fish. That's what it's supposed to look like. And how much is it worth? 100,000. Yes, it is. Yes, it's right here. This whole table. All the tables in this section are what's on this piece of paper. Yes. And then the last one, this figure does not look like the one in contemporary math either out of that book, is an astonished man. And I think he's astonished because he's worth $1 million. I mean, I'd be pretty excited, wouldn't you? Kinsey and I would at least be excited. If you guys have yourself in that position, you're welcome to pass it along to us. We will be excited for you. Okay. So I kind of think this astonished man almost looks like a woman, looks like a dress, right? But, whatever. So there's our astonished man. Typically speaking, the reason students like this number system is because it's easy to work in. All we do is we repeat symbols. So if we want the number 20, we use 2 heel bones. If we want the number 3 million, we use 3 astonished men. Yes, you just repeat the symbol. Now, if you had the number 99,999, you might not be so happy repeating all of those things 9 times. Yes?
Would you do that 9 or 10 little men minus a vertical staff?
Nope, you can't do it that way because that's not how they did it. Yeah. You just have to write out 9 of the pointing fingers and 9 of the lotus flowers and 9 scrolls and 9 heel bones and 9 vertical staffs. That's what it would actually look like.
Okay.
Yeah. All right, so let's take a look at a few questions related to the Egyptian numeration system. We're not necessarily, so in contemporary math, what we do is we move a lot between just like converting numbers back and forth. It's not really focused on that in this section. We're going to do a little bit different kind of approach to this. So here's a taste of that. We're going to do this for each one of our number systems. We have a numeral given. It's 3 scrolls and a heel bone. Okay? We're going to figure out what this numeral is eventually, but that's not where we're beginning. The first question they want us to know is the numeral that comes before this one. So the scrolls are worth how much? 100, and the heel bone's worth 10. And you notice that they're in order, right? The scrolls being worth more come before the heel bones that are worth less. You with me? So if you want to sort of imagine doing this, you would take these values and you want to remove one from it, but I don't have a staff that I can just remove, right? Like one of these vertical strokes. I don't have one of those vertical staffs that I can just remove. So what do I have to do?
Right.
Well, go ahead, Kinsey.
Write the 3 and then 9 of the vertical staffs?
Right. So we take our 3 of the scrolls we already have, and then I exchange my heel bone, basically for like 10 strokes, because that's what it's worth, and then I take 1 away, which leaves me with 9 of these. Pretty okay? So usually the way they ask these questions, one of them is easy to do, like it requires very little effort, and the other one requires more effort. You've done the one that requires more effort. The next one is the easier of the 2 to do. What would I do to get the number that comes after the 3 strokes and a heel bone? Just add 1, right? I don't have to exchange anything. I just tack on to the end the vertical staff. Cool? Okay. And then our question C says, what is the value in Hindu-Arabic numeration system? So you may be able to just look at it and tell, but the numbers as they get harder, you might not be able to. So we're going to write it out in kind of a longhand way. There are 3 of the scrolls, and the scrolls are worth 100, as we said. And then there's 1 of the heel bones, and it's worth 10. And if you multiply and then you add, this gives you the number 310.
So if we were to get this question on our homework, would you want us to write it out first?
I don't care if you do. If it's a simple enough one that you can just see what is going on. Most of them aren't quite so straightforward, right? They're just longer, and so you're going to probably want to write out a little bit just to make sure you don't get the wrong place and wrong number counted, that kind of stuff. So, yeah. Okay. But we also want to go back the other direction, right? This is taking an Egyptian number and writing it in our Hindu-Arabic numeration system. We want to take one of our numbers and write it in their system as well. So that's our other kind of question that we'll see on these ones. So here's our number, 23,145. So you might have to flip back and forth a little bit to remember all the strokes or the symbols that you're going to use. So in the 2 is in the 10,000s place. 2 pointing fingers to represent the 20,000. Do you see how bad my pointing fingers always look terrible? I think they look awful, but thank you. Okay, it's good. And then there's a 3. What is the 3 shape? Lotus flower. You need 3 lotus flowers. Oddly enough, I can do those pretty quick.
Oh my gosh.
Okay, the 1. I purposely chose all the numbers to be different so that I could just say this, right? The 1. What shape is the 1 in the column for? The scroll. This is one scroll. How about the 4? It's in the tens place, which is
4 of the hill.
4 of the heel bones. And then the 5?
5 steps.
5 staffs.
I mean, that was kind of fun.
Okay, so Egyptians really, like, it's very simple, right? It's real simple. I mean, it might be like long, you might have to write a lot of stuff, whatever, but it's very simple how it's structured. But you can see sort of a drawback here, right? This is not particularly like time efficient to write out. Agreed? It's really not. And so there's sort of an issue with the timeliness of it. All right, our next system we're going to look at is the Babylonian number system. And there's only 2 symbols. There is this triangle, and I mean, we think of it as being an upside-down triangle as though triangles have a natural orientation. They really don't, but we think of it as an upside-down triangle. And then we think about it as sort of looking like an arrowhead or something, right? And I will warn you right now that when I write mine, I don't fill them in because that seems like a unnecessary time for me to do. So I just leave them hollow. And if you wish to as well, you may. And I just write my arrow going like this. Again, I don't fill it in. So that's how I'm going to write mine when I write them. If I've got them coming from the computer or to you, or if you're seeing them somewhere else, they're going to be written more formally. Okay, so the triangle shape actually has the value of 1. And the arrow shape has the value of 10. And I do hope that you're sitting here and thinking, so what do we do if it's bigger than that, right? Like that 23,000 number we just saw a minute ago over here. What if I was trying to do that one? What do I do about that? So we don't take up a whole page, actually. What they have in their system, or what they do in their system, is they have a place value system like us, right? We have the tens place, the hundreds place. Like we don't write out, a whole bunch of things repeatedly like the Egyptians do. We have a place value system. But their place value system is a base 60 system. So what does that mean? Well, in our system, we have the ones place, looks like that. And then the next one is tens place, agreed? But they don't have a tens place, they have a 60s place. That's what it means to be base 60. It means all the place values are worth a power of 60. But they don't have 60 different symbols. Thank goodness. Right? That would not be cool. They have 2 symbols. So we've got to figure out how we use 2 symbols to create the numbers like 1 through 59, because the numbers 1 through 59 all have to fit in that one place value, right? How do we do that? Well, they do a repetition of symbols much like the Egyptians did. So if they want the number 2, they do 2 triangles. If they want the number 3, they do 3 triangles. If they want the number 13, they do an arrow and 3 triangles. Everybody good with that as a basic idea for how to sort of deal with the numbers 1 through 59? So the numbers 1 through 59 are just like we would do with the Egyptians. We would just repeat symbols. So again, if we did 59, it would not be super nice, but we would write 5 of the arrows followed by 9 of the triangles. That would be 59. But once we get to 60, we don't have the ability, because that's not how they did it, to just write 6 of the 10 symbols. They don't do it that way. They use a place value system. So I'm going to show you how to do that when we get to that point of it. But first, let's do those questions where we just look at what comes before and comes after. So we've got this very ugly, long list of stuff, right? We do. We're going to do the number that comes before. This is actually the easy one on this one. What would I do?
Just take off one of the triangles.
Right. I just take off one of those triangles at the end. I'll lop it off, right?
So it doesn't matter the order then?
It does. The numbers go from biggest on the left to smallest on the right, just like the Egyptians do, just like we do in some sense too, right? And so we would take off the triangle that's on the far right. So we end up knocking it off over here. So right now, this is a triangle at the beginning. And then there are 5 arrows. So I still have 5 arrows. And then right now, I believe there are 9 triangles there. Is that correct? Yep. So how many do I need to write now, Mackenzie? 8. 1, 2, 3, 4, 5, 6, 7, and 8. You just take one off. Okay, so far so good? So you add one, you subtract one, you just take one off. When you add one, it's going to create 10 triangles at the end, like when we do part B here. So instead of having 10 triangles, we would rather have, or we would prefer, we would have instead an arrow. The problem is that how many arrows were there? There are 5 arrows. So that's going to give me 6 arrows. But 6 arrows is the number 60, and I told you we can't do the number 60 with 6 arrows, right? So what do we do? Well, it looks like this. We're going to do it in a couple of steps so that you have it in your notes to see where these things came from, okay? So we have our triangle and our 5 arrows, and then we have ten of those triangles. We just put an extra one in. But all of these change to become an arrow. But that means I now have 5 arrows, because there's 10 here, and now there's 5 arrows. Not 5, 6, apologize. There were already 5, 6 arrows. There were 10 triangles. So when I have the 6 arrows, I need to move to the next place value and add one more to it. Well, it's a 1 that I'm adding to it, so I would add the number 1 to the number 1, and the answer would look like this.
Wait, I missed something. That's the answer?
It is, but it feels weird. What about it doesn't feel like that should make sense?
That's number 2.
It looks
Because
like
that's
61.
also the same. Ooh, you guys have identified the 2 pieces that are the next question. The next question says, how else could the value found in B be interpreted? Well, it can be interpreted as the number 2. It could be interpreted as the number 60 plus 1, because each of these could be in different place values. The 60's place, the 1's place. That's kind of a problem, and probably part of why we don't use the Babylonian system now.
How is the second? Oh, because the lines underneath. Oh.
Yeah, I put the lines underneath them to identify it. You could say, well, but if it were 61, what you'd really see is you'd see some space in between them. Okay, maybe you would, but that still doesn't preclude the idea from it being the number 2, right?
So whenever you put the 2 triangles, like if you're making the number 6, the first one just kind of like is there as a placeholder? Like
Well,
it
it's not as a
doesn't actually
placeholder.
represent one.
It represents the number 1 in the 60s place. We haven't turned this back into our number yet, so let's actually do that, because that's, I think, the next part of it. What is the value in Hindu-Arabic numeration system, the one we started with? So we're going to take the number that we started with, which was like this. Terrible triangles at the end, forgive me. So what we do is we break apart our numbers when it goes, like this is the number 1. Let me write it in red. And then these are all 10s, right? And then we switch to the numbers 1 over here. Well, bigger before smaller, so the 10s before the 1s, that's good to go. But at the point where we have a smaller number, namely the 1 before the 10s, that changed place value. So this right here is a separate place value from this one. This is the 1's place, and this is the 60's place. It just has lots of stuff in it. We don't do that in our system, right? We put a single digit in each individual placeholder. And in fact, children often struggle with that, especially when they're learning to do 2-digit multiplication. And they want to put something like 11 into the single place underneath it because they added 7 and 4. And you're like, no. You have to regroup it, right? You can't have a 2-digit number showing up underneath there. But you can in here. They can have multi-digits showing up in their system. So this is the number 1 in the 60's place. And then it's the number 59 in the 1's place. because they have a base 60 number system. Right here, it means that the first place value on the far right is worth the 1, and the second place value is worth 60, and the next place value would be worth 60 squared. It's also worth noting that over here, Mackenzie, we're assuming that we're in the 60s place, but nothing says it couldn't be the 60 squareds place. There's no way to distinguish that in their system. We know it changed place value, but how far did it change place value? Just to the 60s place or something bigger? Our assumption for what we're going to be doing in class is that it just changes one place value, but the reality is that you wouldn't know that if you were working in their system in that day and age. This isn't especially helpful. I hope you're getting that feeling. You've got multiple possibilities. So if you're doing bookkeeping and somebody owes you, oh goodness, my screen went off, just a second. Okay, we're back. So if you were doing bookkeeping in that system, right, how would you tell somebody and knowing for sure how much money they owed you when the number 2 and the number 61 look the same, right? How would you do that? And I don't have a real good answer for you. I don't know what they did in that case, but I know it must have been confusing because it doesn't work like that in their system to show those distinguishing, values. On this, however, I have 60 plus 59 to give me a grand total of 119. So what we really wanted over here was one number bigger than 119 should be 120, right? And the reality is that this number is the number 120, but it's also the number 2, and it's also the number 61. That's not good. No, not good at all. It's not a confusion in the sense of things that I'm going to throw at you. That's not the point. What I'm trying to point out to you is that there's flaws. And this is one of those innate flaws. It won't come up as being a problem in any of your work. There's not going to be a confusion in it. That's not the point. The point is simply that there is a flaw in their system, and this is what we can see it to be. Let's go the other direction. The other direction, I wish I could tell you is like super simple. It isn't, but it's going to be the same process that we're going to use a lot of times. So the first time we show it, it's going to look weird. But as we do more of them with the same processing, you'll begin to understand how it's piecing together. So just bear with me for the first one with the Babylonians, and we'll see it show up again when we do the Mayans. We'll see it show up again at the end of the section when we do just random base systems, okay? All right, so the way that we do this is that we have a base 60 system. So the ones place, we mentioned the 60s place, 60 squared, 60 cubed, and so on. Well, 60 is just 60. What is 60 squared? Grab a calculator if you need it, because you might for at least the cubed part. At least, what is 60 squared? 60 times 2. We want 60 squared. It is. It's 3,600. How about what is 60 cubed? The generic answer is much bigger. What is 60 cubed?
260,000.
It is. Okay, so taking a look at those numbers, 1, 60, 3,600, 216,000. We don't need anything that's bigger than the number that we were given. We're given the number 43,205. So what do we not need from this list? Yeah, we don't need the 60 cubed one, right? Yeah, there's no need for it. So our value will have 3 places. We're going to have a 3-place system. And we're going to use these numbers that are underneath, 3,600, 60, and then the 1. We're going to use them and we're going to do some division. The kind of division we're going to do is might not look like some division you've seen before, but it builds together much like things you've done before. So we're going to start with it looking very much like you've seen before, but with your aid of your calculator, I want you to figure out how many times does 3,600 go into 43,205. I want a whole number. What's the whole number you get? I know there's a whole number and a decimal. I just want the whole number part, 12. Okay, and now I want us to take 12 and multiply that by the 3,600. 12 that's on top that you gave me, and want to multiply that by the 3,600 in front.
43,200.
43,200, and we're going to subtract. When we subtract, what do we get? 5. That's lovely. It's so close. We're going to divide again, so I'm going to write this over here. Sorry, I shouldn't have written my 12 on top. I missed one piece of this. We're going to write the 12 over on the side because we need to be able to have the subtraction going on in the middle. We're just to write with the quotient part on the top that would have been on the top on the side. I'm sorry. I feel like it looks like top hats, by the way. So, all right. What's the next power if we're going down the list?
Next power.
Yeah, like the next value that is in my list of 60s up here. What is my next one? I divided by 3,600. What's the next one? 60. And I know it doesn't feel like it's necessary to do this step, but it will be later, so I want us to just get in the habit of doing it. We're going to be dividing by every value in the list. Obviously, 60 doesn't go into 5, so 60 goes into 5 0 times. 0 times 60 is 0. 5 minus 0 is 5. And again, I know that looks silly, but you'll see why when we get to the point where it's super necessary later. So if we just always do it the same thing, it's there. What's the last number I divide by?
1.
1. And how many times does 1 go into 5?
5.
5, and 5 times 1 is 5, for a remainder of 0. We will always get remainder of 0, but our last step always needs to be division by 1. So we don't stop until we've divided by every piece of the power list of powers till we get down to 1. Okay, these numbers over here, 12, 0, 5. In a very real sense, they're right here. This is the number 12, this is the number 0, this is the number 5. Okay, that's what they are. There are 12 60 squareds. There are 0 60s, and there's 5 1s. How do we write the number 12 with the triangles and arrows that we have? An arrow, that's worth 10.
And then 2.
And then 2 triangles. So an arrow is worth 10, 2 triangles were worth 2. This is the number 12. How do we write 0?
Nothing.
There's no symbol. That's a problem. It's not the only people who have a problem by not having a 0, by the way. They're the first ones we've seen today. It didn't seem to really matter that the Egyptians didn't have a 0, right? No, not really. It didn't matter because the way the symbols were created, but here it matters. We're going to skip over it. Doesn't matter that it's there because we don't have a way to write it, so we're going to move on to the 5. How do I write a 5? 5 of the triangles. This is the answer. But what else does this actually look like?
18.
Looks like 18. And even if, best case scenario, there were like this separation that you knew for sure that these are like separated from one another like that, if you knew that, I'm not asking you to underline it, but if you knew that, it still wouldn't necessarily mean that it looked like the 43,205. It would also look like 12 60s and 5 1s, wouldn't it? Because there's no 0 to hold the placeholder of the 60s place. There's no way for me to know looking at this that there's a 60 that's missing. And again, that's the problem. I'm missing placeholders. I'm missing the separation pieces. Now, I don't have commas or things like that. I don't have that kind of stuff here. So I have a problem with what's going on. This is not good. It's not good. Okay, let's start Mayans. I don't know if we'll finish the Mayans, but we can at least start them. The Mayans have 3 numerals.
Is that a pie?
No, it kind of looks like one. It looks like a biscuit or something. A shell is what they usually call it. And it's not always drawn quite like this either. The book that I use for contemporary draws it a little different. But the value of the dot is 1. The value of that horizontal line is 5. And the value of the shell is 0. So lo and behold, we have a 0. That should help some things, and it does help some things. It's not going to help all the things, though. We're going to still have a problem.
Yeah, well, no,
We only have 3 symbols, right? I mean, this can't be good. All right, so let's just see. First, some information. They have a place value system. So we have a place value system, Hindu-Arabic. The Babylonians had a place value system. It was base 60. The Mayans have a modified base 20 system. Do you know why we have a base 10 system? Think for a second.
because we have a base, a 10 place value system.
But why?
So 10 numbers.
Why?
We have 10 fingers.
Because we have 10 fingers. Totally legit. We have 10 fingers. So why do you think maybe that the Mayans had a base 20 system?
Did they have
They
20?
use their toes.
Use their toes.
Oh.
Yeah, fingers and toes, right? Walking around barefoot and sandals and things like that. Fingers and toes. There's the 20 coming about. There's something else that's interesting about their system. We'll get there in a little bit. Based on the 20 system. This also says that it's a modified base 20 system. What that actually means is that it's not like our system is the 1, 10, 10 squared, 10 cubed, and so forth. The Babylonians was 1, 60, 60 squared, 60 cubed. The way that their system actually works is it's 1, 20, and then it's 20 times 18. Now, I'm going to show you how that works out after I finish other pieces here, but we'll come back to that modified part in a sec. It is written vertically. So their smallest place values on the bottom, and their largest place values on the top. Okay, so usually it's the biggest is on the left and the smallest is on the right. Their smallest is on the bottom, the biggest is on the top. And dots are written above bars. Okay, so example, if you had the number 6, the way you would write the number 6 would be a bar with a dot on it.
Well, that's not small storage.
It's not, but it's the smallest place value on bottom. For example, then if you had the number 21, you'd have a 20, that's a dot for the 20's place, and then you have a 1, that's a dot for the 1's place. So there's an inherent, I don't know if this is showing up well enough, separation happening here. The dots are above the other dot. This is the 20's place. Yikes, I need that one right there. This is the 20's place, and there's 1 in it. This is the 1's place, and there's 1 in it. This makes a total of 21. So it's dots above bars, higher place value above lower place value. So like if we took our number, say 345, in their system we would write 3 over 4 over 5. Right, 3's not small. 3's not bigger than 4. You know, that's not what we're talking about. But the 3 is in the hundreds place, so it's in the top spot. The 5's in the bottom spot because it's the 1's place. So far, so good. Okay. Dots above bars, modified base 20. So let's go back to the modified part of it. So we have the 1's place as our bottom place value. We have the 20's place as our second one. This is all just entirely too large. Move this over. After that, they have 20 times 18. So grab a calculator, tell me if you know. What is 20 times 18? 360. So I'm going to pause right there for a moment before we go to the next place value. Any idea why they would have wanted 360 as opposed to 20 times 20, which is 40? There's something that's sort of classically attributed to the Mayans that's really, like historically, like a big deal. That has to do with the number 360. Days.
But was it 360 before?
Okay, so you're on the right track, Kinsey. So the Mayans were specifically noteworthy for their calendaring. They're the ones, if you'll remember, who predicted the end of the world, so to speak, in 2012. Obviously, they were wrong. That's the Mayans, yeah. So, yeah, I mean, they were obviously wrong. But the 360 is coming from what their approximation was at the time of the number of days in a year. That's where it's coming from, 360 days in a year. So they wanted something that made sense in a calendaring sense, and so 18 times 20 did that, for 360 place value. What happens after that is that they just power the 20s. So then they've got 20 squared times 18. And then they have 20 cubed times 18. So they do powers of 20 after that. It's just that they have this one sort of random like times 18 in their third place value. Okay, so we're going to look at A and B and then we'll stop. It'll be really quick. Here's our number. We have 2 dots in a line. Just for the sake of having talked about this, what is the 2 dots in a line going to equal? Y'all know? 7. And what about the 4 dots in a line? 9. And the reason that these are separated is because the line for the top value turned into a dot for the bottom value, right? So that's how we know we're separating it. It's because now I have a line over a dot. So there has to be a separation right here between place values. So what do I do if I'm trying to take this value and find the number before? Well, I look at the lowest place value. It's a 9. What do I have to do to change 9 into something 1 smaller? Take a dot away. It's easy to do that one. That's the easy one. So the top number stays the same, the 7, and the bottom number changes to 3 dots. They don't look quite like dots, but 3 dots in a line for the number 8. This is the number before. So what would you do to get the number after?
Add 1.
You'd add a dot, which would then give you 5 dots, but 5 dots would be a line. So you would end up having the 2 dots in a line here, and then you'd have 2 lines down here, and do you see a problem? What's that number?
That's 17.
That looks a lot like 17, right?
Yeah.
That looks a lot like 17, but that's not what it was supposed to be. What it was supposed to be is representing that this is 10 and this is 7. That's what we wanted it to be. But 10 and 7 is not 17 when you're in place values. This is the 1's place, and this is the 20's place. So this is actually supposed to be a different number than 17, but it looks suspiciously, the way that it's written, like a 17. So we'll pick back up there next time.